And we've seen this with an x cubed graph. And I can tell you that almost all of you have been drawing an x cubed graph a little bit wrong. Probably when you draw your x cubed graph, you went like this. And be like, that looks like an x cubed graph. And it's not quite right because right here, if I drew a tangent at that point right there, it looks like its slope looks like a positive slope or something. When in reality, it flattens right out at that spot. And we would say that it has a bend in the graph, and that slope is equal to 0 at that point, but the graph doesn't have a maximum or a minimum. Instead, it changes from something that we call concave down to concave up. And I think of little smiley faces. Concave down is like you're down, you're sad. Concave up, you're positive, you're happy. So we're going to find out that those things come into play as well. So how do we know if we have a stationary point of inflection? Well, we would still have the fact that our slope is 0. If our slope is 0, that always defines a stationary point. But now, instead of a max or a min, if at that point we draw our number line for our derivative, and we put that point x1 on there, and as in our x cubed graph, it's increasing, then increasing again, then you would realize, oh, it can't be a max, it can't be a min. It's still a stationary point because the first derivative is equal to 0, so it must be a stationary point of inflection. And this is something we're going to also add to our graphing, is that our second derivative will always find inflection points. And an inflection point is exactly this idea. For example, on this one, inflection point would be about there, in that whenever you change from concave down to concave up, we call that point an inflection point. And those will always be found with our second derivative by making our second derivative equal to 0. So with a stationary point of inflection, your first derivative will equal 0. It will either stay increasing or stay decreasing, and you'd also find that your second derivative is equal to 0. So let's look at the following graphs and see what we can come up with. So when graphing completely, and I'm going to start teaching these graphing as a holistic thing of everything that we're going to do, we are going to use some information from previous years, sort of preliminary stuff. We've done that on a couple of graphs. We're going to check, are there any known permissible values? Are there any asymptotes? And easy points and important points to put on a graph are intercepts. Can we find the intercepts easily? Or would we have to use our calculator or Desmos to do that? So for this one, as far as preliminary stuff goes, I think it's really easy to see that the y-intercept, when you plug in 0 for x, is 0, 1. Looking at that equation does not look easy to factor to find out x-intercepts. It's an x cubed graph that has no asymptotes. So sort of preliminary stuff, I look at asymptotes and intercepts. What are the things that I know? Now that I've done the preliminary stuff, I can go to my first derivative. And I can think about my first derivative test. So there's my first derivative. Set my first derivative equal to 0 to find critical points. Factor out 3x. So on my number line, I would have -2 and 0. This is my number line. for my derivative. So if I plug something into my derivative, and here again, I really like to plug things into the factored version because it really helps think about positives and negatives without having to do a lot of mental math. For example, something less than -2, -3. That will make this factor negative and this factor negative. Plugging in -3 makes both of those negatives. It's pretty easy then to see that that section, a negative times a negative, will be positive. Something between -2 and 0 would be -1. 3x would still be negative, but now -1 would make this factor positive. A negative times a positive. That's decreasing. And then plugging in something bigger than 0, like 1, makes them both positive. So it goes from positive to negative to positive. This one has no stationary points of inflection. It only has maxes and mins. And so we would be able to say from the first derivative test, since at -2 it's equal to 0, and since it changes from increasing to decreasing, we know that -2 comma something is a local max. Okay? And I think this is the reason why students make mistakes in explaining, because once you've done this, and 99% of the time, you will not have non-permissible values in your equation. So you just get used to, oh, it's a max. Oh, this is a min. And you're right 99% of the time. And so when you go to explain it, sometimes you forget to say in my explanation that f prime of -2 equals 0, and it changes from increasing to decreasing. Now to find the y-coordinate of your max, anytime we're trying to find a point, the point relates to our original equation. You have to plug that value into your original equation. -8 plus 12 plus 1, we would have the point -2 comma 5. And for our minimum at 0 comma something, and we've already figured out that that was our y-intercept, that would be our minimum. And so on this graph, we would have 0 comma 1, -2 comma 5, we would have these points as a max and min. We know that our graph has to be increasing then decreasing, then increasing again. And what you try to do is try to draw a curve as smooth as possible through those points that you have to draw your final graph. Now, what we're going to add to this soon is finding this point here, where it changes from from concave down to concave up. And just to show you that quickly, because it's easy on this one, we'll be able to find our second derivative from our first derivative. I guess I'll keep the notation the same. My second derivative would be 6x plus 6. And setting that equal to 0. Tells me that it happens at -1. And we will also be making a number line for our second derivative plug in where it's -1 and any non-permissible values. And in the same way you check positives and negatives with your first derivative, we'll be checking positives and negatives with our second derivative. So for example, if I plug something in less than -1 into my second derivative, it's negative, and negative makes it sad. So we have concave down, which, as you see from the graph that we drew, did that naturally. And it looks like where I drew the point was pretty accurate, at -1 comma something. If I plug in something bigger than -1 into my second derivative, this is positive, and it's concave up. Again, if I wanted to find that y coordinate, I would plug in, and it happens to be at -1 comma 3. And this is probably just coincidence. But where I looked on the graph where I thought it changed from concave up to concave down, and I didn't have the point of inflection already figured out, look how accurate that point ended up being. If you have your maximums and your minimums, and you draw a smooth curve through those points with increasing and decreasing, your graph is really quite accurate. And I found my inflection point, I labeled it on there, and it is actually right where it was supposed to be, based on drawing a smooth curve that naturally occurred at that right point. Okay, let's do this next one to see, because this one will have a stationary point of inflection. Okay? First of all, preliminary stuff. This graph has no non-permissible values, so no asymptotes. This graph would be easy to find a y-intercept. Plug in 0 for x, and you get 0 for y. And this graph would also be easy to find x-intercepts. A reminder, how do you find x-intercepts? You plug in 0 for y. I'm going to factor out a common factor of x cubed, and so I would get x-intercepts at 0, 0, and I wouldn't have had to write 0, 0 again, because I already wrote it down as a y-intercept, but just to list it there, we have an x-intercept at 0, 0, and 4, 0. So this is preliminary stuff from previous years. If we can find x-intercepts, in this one we could, great. If you can find y-intercepts, they're always fairly easy to do, perfect. Look for asymptotes, and then we'll get into our derivatives. Just a note on notation, I like to try to find all the different function notations I see in different textbooks. If you have a notation like this one, which I don't really care for this one, you can change it afterwards. I would go, for my derivative, I would just go, okay, I'm going to write this one, f prime of x equals. You're going to forget some of your derivative rules, because in curve sketching, we go back to just easy derivatives for a while. So you might have to make sure that you go back to your derivatives unit and like, oh, I should do a complicated product rule or chain rule every once in a while using natural logs and secant squared and something like that just to practice. Okay, so here's our derivative. We set our derivative equal to 0. You can factor out a 4x squared here. And so we get 2 points, x equals 0 and x equals 3. We can put those onto our number line for our derivative, and plugging in something less than 0, like a negative. Again, I'm going to use my factored form. Can you see that that 4x squared is always going to be positive? Because when you square a number, you get a positive result. So even though I plugged in -1, this is still negative. It goes positive times negative. This is negative. It is decreasing. I plug in something between 0 and 3, like a positive 2. This is still positive. This is still negative. We're going to have a stationary point of inflection on this graph. And then something larger than 3, like 5, We'll make that one positive this time. So, our points. We are going to have 0 comma something and 3 comma something. From our first derivative test, since f prime of 3 is 0 and it's decreasing and increasing, this one is a min. And this one that stays decreasing but still equal to 0 is a stationary point of inflection. And I don't know, there's no good, no good abbreviation for that. Like min, as soon as you write min, everybody knows minimum. I don't know how we write inflection point. Maybe. Would that be a good abbreviation for inflection point? Mathematicians do not like to write extra stuff down, and stationary point of inflection that's practically an essay. So, now as far as finding our values, we already knew that 0, when we plugged it in, we'd get 0. 3, I go back to my original equation, I plug in 3, I get 81 minus 108. I don't know if that's right. Yeah, okay. So, we've got our min, we've got our stationary point of inflection. Technically, this is what we have so far. Oh, I am going to cheat a little bit on my x-axis and just go 10, 20. Again, when we go to graph things, we have to think, what information do I have? The information that I have already is I knew that my x-intercept, y-intercept was 0, 0, and 4, 0. And I also know that I have a min at 3, negative 27. So I had to sort of think ahead of time of what kind of scale I wanted to use on my graph. Now, for graphing this one, because this will be the first one that we officially graph with a SPOI, a stationary point of inflection. And what we need is at this stationary point of inflection for it to flatten out completely. So our graph is going to need to come down, flatten out, come down, hit our minimum, and then go back up forever. And again, once we add the very last thing in graphing, which would be our number line for our second derivative. And for our second derivative here, we would have found these 2 points, one of them 0, the other one unknown, and we would have found out this section was concave up, then concave down, and then concave up again. And having these concave up and concave down sections will help us graph it even better. Because what I'm going to suggest, I'm going to switch my color of my pen to purple. And I'm going to, first of all, re-highlight this point, and the inflection points. That's what you would start with. You would have those 4 points as key points in your graph. The concavity is going to help you graph it even better than the increasing and decreasing. Because sometimes you're decreasing, you might make your line too straight, or not show enough curve. But if I start with my concavity, and left of 0, I know that it's concave up, I would actually start at 0 and draw that section concave up. And then this section, I'd start at 0 and concave down, and then concave up again. And by doing that, switching from concave up and concave down at the inflection points, you will get that idea that it's flattened out right here at 0. Okay? And now I'm going to take you back to chapter 1 of grade 12, not chapter, polynomials graphing in grade 12. One of the things that you learned in grade 12 graphing is sometimes if you got a 0 that happened more than once, I don't know if you remember this, we would say in grade 12, this one had a multiplicity of 3 because that factor of x happened identically 3 times. And anytime you had a multiplicity bigger than 1 that was an odd number, in grade 12 pre-calculus, we talked about the graph having an x-intercept but bending at that x-intercept. Well, now we see in calculus that that bend is actually a stationary point of inflection. But it would be like, that's way too much for grade 12 to have 4 words already, so we just think, let's just call it a bend. It bends in our graph, perfect. Remember, sometimes it bounced off the x-axis. If you had a multiplicity that was an even number, like a 2, a 4, or 6, when it hit the x-axis, it bounced off of that, okay? In calculus, we don't have to worry about bends and bounces as much anymore because we will naturally find them to be stationary points of inflections when they bend, and we will naturally find them to be maxes or mins if they bounce. And if they just happen to do that at an x-intercept, fine. But it's sometimes nice to see these connections to things that you've done in the past. So you've learned that in grade 12 about the bounces, the bends, and the multiplicity. Now this comes back and we see it here. The nice thing about calculus is you know from transformations that I could take this same equation and just put a +1 at the end and move everything up 1, which would move this stationary point of inflection up 1. And in grade 12 pre-calculus, you wouldn't be able to find it because you could only find bounces and bends if they were x-intercepts. But calculus lets us find them wherever they are. Okay, so with that, we are ready to do our next section.